Today we're going to be doing everybody's favorite, half-life. So before you get started, you're probably going to want a separate sheet of paper to do all the work because for this worksheet you're going to have to show all the work. So we do use the chart the way I taught you. So we always start like this, and you're going to have half-life, time, mass. Always start with double zeros, and this can go down as far as you think you need. I'll just go down a few, and if I have to add more, I add more. So for number one, it says, and you should have your reference tables out and open, most likely to table N. It says, what is the number of hours required for potassium-42 to undergo 3 half-life periods? So in order to do this problem, I need to know the length of a half-life of potassium-42. So if you go to K42, which is right down here, 42, it's 13 or 12.36 hours. So one half-life is 12.36 hours. So the next half-life is going to equal 24.72 hours, and then the next one is going to be 37.08 hours. So 3 half-lives will take that many hours, and we're done. And it turns out I didn't need the mass column for this, and sometimes you don't. It depends on the problem. Sometimes you might only need 2 out of the 3 columns, and it's typically going to be the first column for sure, and then either the first and the second or the first and the third. And so that's typically how these problems get worked. So let's do number 2, and then I'm going to do a couple more where you have to go backwards, and then we're done. So for number 2, it says an original sample of a radioisotope had a mass of 24 grams. So let's set this up first. So notice they said the original sample is 24 grams. So that's my original sample. Now I don't know what I'm doing or how far I'm going down, but let's figure it out. It says after 6 days, only 3 grams remain. So at some point, this 24 is going to turn into 3. So I can do that right now. I can do, all right, half of 24 is 12, half of 12 is 6, half of 6 is 3. So I got it. I got 24 and I turned it into 3 grams. All right, so that's easy. And then they said after 6 days. So that means that this part took 6 days. So I can do it 2 ways. I can just do 6 days over 3 half-lives, and that's going to give me 2 days per half-life, which is actually my answer. That's the length of one half-life. You could also set up the ratio, if 3 half-lives equals 6 days, 1 half-life equals X days, and then solve for X. I like it this way. You just divide those 2 numbers. If I wanted to go back and check, I could just add in the half-life and see if it adds up to the right amount. So that means 1 half-life would be 2 days. 2 half-lives would be 2 plus 2, so 4 days. And 3 half-lives would be 4 plus 2 again, 6 days, and it works out. So that's problem 2. Let's jump down to problem 9, because 9 I think goes backwards. So let's see how this works. I'm actually going to put it on the back so that I can put it back to the top and you can hopefully see it. So here's number 9. And it says after 62 hours, 1 gram of the radioactive sample of K42 remains unchanged. What's the mass of the original sample? So first I need to look up the half-life of K42, and we did that. It's 12.36. I think I'm going to go a little further on this one. And so after 62 hours, 1 gram remains. What's the mass of the original sample? So the first thing I need to do is I need to figure out how many half-lives fit into 62 hours. So I'm going to start adding up my 12.36 to get to 62 hours. So if I do it once, it's this. If I add another 12.36, I get 24.72. If I do it again, I get 37.08. If I do it again, I get 49.44. If I do it again, I get 61.8. I put the lines in there just so I can be as neat as possible. The common mistake I see is putting too many numbers and then like messing up which line goes with the mass. And so if you're not neat, you can make silly mistakes here. Now notice, I didn't get to 62 hours. I got 61.8. As far as I'm concerned, that's the same thing, right? That's pretty much 62 hours. So we're not going to go to a sixth half-life, because if we did a sixth half-life, we'd be way over. It would be 74.16. So 61.2 is or 61.8 is basically 62 as far as we're concerned. So we're going to stop there. And then they said 1 gram is what remained, right? So that means down here we were at 1 gram. So now we've got to go backwards to get to the original amount. So normally you would half it to go forwards. To go backwards, you do the opposite of halving. So instead of dividing by 2, you multiply by 2. So it's going to be 2, and then 4, and then 8, and then 16, and then 32 grams. And that was the original amount. All right, because if I started with that amount, I'd have halved it 5 times. I would end with the 1 that they told me I ended with. And that's all you really do. Let's go to the back and do one more problem. Maybe 2 more. One that I want to do is number 15. 15 tends to throw people off, so let's make sure we go over it. So 15, it's really like 2 problems in one, okay? It's very similar to the one we just did. Well, actually it's not. It's similar to the original ones, but they add in this whole weird year thing. So this is how, I remember, if you remember in the notes, I said half-life can be used to keep track of time. This is really how it's done. So it says if 8 grams of a sample of cobalt-60 existed in 1990, in what year will the remaining amount of cobalt-60 be 0.5 grams? So if I look up the half-life of cobalt-60, it is, let's see, 5.271 years. So 1 half-life would be 5.271 years. And let's see what we're doing. 8 grams existed in 1990. That's the original amount, right? So therefore, I'm going to put 8 grams in the original. And then in what year will the remaining amount be half a gram? So I'm going to half this until I hit 0.5. Okay, and that took 4 half-lives. So now I need to know how long that was. So this is where my half-life comes in. So this would be 10.542 15.813 21.084. So we're just going to call this 21 years. Now that's not my answer, because remember, what they went back and told me was that at this time, the original, this was 1990, okay? And then the amount of time it takes for half of that sample to decay to for the 8 gram sample to decay to 0.5 grams is going to be 21 years later, rounded. So if we started in 1990, when did we end? That would have been 21 years later. We'll just round it to 21, and it would be 2011. And so that's how you do that problem. The last one I want to mention is problem 19. This one's pretty easy. Which radioisotope has would have the greatest mass remaining after a period of 100 years? Well, the answer is whichever half-life would decay the least in a 100-year period. You can figure that out. And then which radioisotope would have the least remaining mass after 100 years? Well, that would be whichever one halves the fastest. Meaning if your half-life is only like a second, then you're going to half like, I don't even know how many seconds are in 100 years, but you're going to half that many times, right? And if your half-life happens to be, you know, 100 years, you only half once, and if your half-life happens to be 200 years, well, you don't even half once. You don't even get to a quarter, right? Or you get to a quarter maybe. And so you just have to figure out which ones have the longest half-life, they decay the slowest, and which ones have the fastest half-life, they decay the fastest. So, or the shortest half-life decay the fastest, and the longest half-life decay the slowest. The rest of the problems you should be able to do on your own. If you have any questions, you can obviously message me. We'll be definitely working on this in class. If you are absent, though, it is going to be a lot of work, and make sure you show all your work. I want to see the chart for every single problem, obviously except 19, because that one doesn't really get a chart. That's just more of a conceptual problem.